Hi, I am Luke Oxley from Team 6498, and in this video I'll be discussing the sensors used on our robot. And the content of this video contains object detection sensors, position sensors, and vision. To start things off, what is the point of using sensors? First of all, the driver has limited abilities. This is because they are a human, meaning that they have a large reaction time and they cannot multitask very well. The goal of these games is efficiency and speed. This is because teams will generally be able to score points, but what will make you better is scoring quickly as possible. Also, sensors allow for more automation. This means that more complex mechanisms are possible, such as an automated ball system or automatic shooting, and this helps to fix the fallbacks of the driver. First off, object detection. One of the most simplest sensors is the limit switch. This requires physical contact with the object, and there is a metal lever, such as on this sensor, that can be bent to change where the object hits the sensor at. However, these are prone to damage because there is physical contact. These are generally useful for homing mechanisms. And one thing to keep in mind, if you look at this sensor, it does have 3 pins. One is a common pin, and the other 2 are normally open and normally closed. Normally open means that whenever the sensor is open, it does not allow current to pass through. However, the normally closed pin means that whenever the sensor is open, current can pass through. Generally, what we use on our team is normally open, but it does not matter as long as you set up the program correctly. One of the most common that we use on our team are photo eyes, and there are 3 kinds. First is the reflector kind, to where this photo eye requires a piece of reflective tape to be taped on the other side of the sensor, so that whenever the sensor emits light, the light bounces off and back into the sensor. The good thing about these sensors are that they do have a small cone, and when I say cone, it's kind of like how large the range or the area is based on how far away you are from the sensor. So if you have a laser pointer and you point it at something really close to you, the dot's pretty small, but if you point it at something far away, the dot gets very large. Now the next kind are the diffuse sensor. These do have a large cone, but that means they're also more forgiving, and they do not require a piece of tape to be taped on the other side. Now they do come in adjustable kind, to where they'll have a tiny screw that you can turn to adjust the sensitivity or the range that the sensor sees the object at, or they come in fixed field, to where it'll only sense the object if it's within, like, say 3 inches or whatever the sensor specification is. Now the next kind is the through beam, and this means that there's a sensor that sends out the light and a receiver on the other side that receives the light. Now these are the most accurate because if an object is there blocking the view, it's definitely going to sense the object. And these are usually used in safety applications in factories. However, these do require 2 install points, and because we don't really care too much, we don't use these on our robot. Next is the inductive or prox sensor, and this senses a change in magnetic field, meaning that it can only sense metal objects, and it is a really short range. On the sensor on the right, it's about 2 or 3 millimeters away, and the sensor on the left, this is a pretty large sensor too, it's only like a couple inches max. Now the good thing about these is that there's no physical contact required, and that they are a pretty good replacement for limit switches. Next is the ultrasonic sensor, and this senses the distance that an object is away from it based on the time of flight of sound. So to do this, it emits a sound wave pulse. This sound wave then bounces off the object and is received by the sensor. Then the sensor calculates the distance based on the time of the wave for the wave to travel and the speed of light, or the speed of sound. Now this does require the object to be pretty close to perpendicular. This is because if the object were at a weird angle, then the sound wave would bounce off at a weird angle and miss the sensor entirely. Now, one of the bad things about ultrasonic is that they do have a pretty large cone and that they're not really super accurate. They'll just give you a general idea of where the object is. Next is LiDAR, and this is kind of like an ultrasonic. However, it measures the time of flight of light, which is pretty crazy because light travels so quickly. And the good thing about these is that there's almost no cone since it's a laser, and they're pretty accurate even at long distances. Now, one thing to keep in mind when wiring industrial sensors, these are our photo eyes or prox sensors. They come in PNP or NPN. Now, this means that a PNP sensor, whenever it sees an object, it'll output a positive voltage. Now, this is a problem because our Rubber-Rio can only read up to 5 volts, but these sensors run at 12 volts. So to use it, you'll have to do a pull down or a voltage divider using resistors. Now, NPN, whenever the sensor sees an object, it grounds the output pin, meaning that it can be wired directly to the Rubber-Rio and there's no voltage divider required. So whenever you have a choice, try to use NPN because it's much easier to wire. Now I'm going to be talking about the sensors used to measure position. Now in terms of rotational motion, the first is the optical encoder, and this includes a disc with stripes that is mounted on the end of the shaft. And whenever the disc rotates, it has an optical sensor that senses whether or not it's on a stripe or not. And it does have an A and B channel, so it does have 4 wires that you need to use to wire it up. Next is the magnetic encoder, and this requires a magnet to be mounted on the end of the shaft, but there is no physical contact between it and the moving object. One advantage to these are that they are available in a CAN bus kind, to where you can wire it in series with your motor controllers, and this is much easier to wire. The third kind is the absolute encoder, and this is mounted directly to the shaft. And it usually has an analog output, but you can also get it in a PWM or pulse width modulation output as well. Now, one thing to keep in mind about absolute encoders is that they are not really rated for a really high RPM, but the other two are fine for high RPMs. The next kind is linear. Now you can use ultrasonic or LiDAR, the ones that I previously discussed, or you can do a rotational conversion to where you have a string, this is on the left picture, that whenever you pull the string out, it'll rotate a shaft that the encoder's on. Or in our right picture, this is from our 2020 robot, you can have a rack and pinion to where whenever the rack moves up and down, it rotates the pinion that the encoder is mounted on. Now I'm going to be talking about vision systems. One of the most important things to keep in mind for vision is the lighting, and you'll notice that the limelight especially has a really bright green light, and the reason why this is green is because most of the colors on the field are red or blue, and the green helps to provide contrast. Also, the reason why it's so bright is because this allows you to change the exposure time of the camera so that it lets less light in, and it'll only pick up on the super bright lights. You can see in this picture, it sees everything. It only sees the ceiling lights and the target. Now, the green light does have to be very close to the lens. This is because most of the vision targets on the FRC field are made of retroreflective tape, And this tape works kind of like a road sign, to where whenever the light hits the piece of tape, it's bounced back in the same direction it came from. So you want this light to be close as possible to the camera so that as much light is reflecting back into the lens as possible. Next is the placement of the camera. Now the angle is very important because you want the target to be visible whenever the robot is close to the target or far away from it. And you also want to try to angle it so that there's a large variance in the position of the target whenever you move. In terms of location of the camera, we generally place it high up and centered on the robot. And the reason why it's centered is because this helps with calculating exactly where the target is relative to the robot instead of doing some unnecessary translations. Now, if this camera is going to be used for driving, it's really helpful to have some part of the robot visible in the frame as a reference so that the driver can kind of know where the robot is in the frame. Now, in terms of placement, you want as much height difference as possible between the target and the camera. And this is because this allows for greater accuracy when measuring the distance that the target is away from the robot. This means that if your camera is the same height as the target, whenever you move forward and backward, the target's not going to change position in the frame, so you won't be able to calculate where it's at all. And that wraps it up on my sensor video. Thanks for watching.